Okay, looks like we're recording. Okay, so last time, here's where we left off. We did a bunch of stuff with change of variables, and I had asserted a formula for the stretching factor. I just kind of put it on the page, right? Gave you no justification for it. So I do want to give you a quick motivation for where that formula comes from. I just think you should kind of see this argument. So the big idea is, now this is not to scale, of course. This is sort of expanded. So this is not the whole domain. This represents just one of our little itty-bitty little, rectangles, a little piece of the domain. And then this is its image over in the target. So also itty-bitty and approximately a parallelogram, because on the differential level, functions are described by the derivative matrix, and derivative matrix is linear, right? So a linear image of a rectangle is a parallelogram. Now, that's an old fact of linear algebra, and not hard to prove, by the way. Okay, so what I want to do is I want to know by what factor is this area bigger than that area. And you can kind of see how the algebra is going to work out. You can see I've derived that factor here. And in particular, that's what you multiply by this area, du dv, to get this area that I'm calling dA. That represents area in the xy plane, namely in the target. Okay, so how am I going to show that this works out? We're going to do this just by computing this area. Just brute force. That's a pretty straightforward calculation, in fact. Of course, areas are understood, area of a parallelogram is computed by the edge vectors. Remember, you take the edge vectors and you take the absolute value of the determinant of the matrix where those edges are the columns. Right? So where do these formulas here come from for those edge vectors? Well, these formulas are actually pretty immediate. If you look at, let's see here, let me get rid of the mess here. If you look at where those edge vectors come from, they are literally the images of these edge vectors. Right? And we have a long since established relationship between input vectors and output vectors, aka input changes and output changes, right? The derivative matrix is what relates them. So you'll notice that that's all that's happened in computing. What do I have to do to turn those edge vectors into these edge vectors? I'm just multiplying by the derivative matrix. That's all it is, right? So that's where these edge vectors come from. Area is the absolute value of the resulting determinant. And at this point, it's just a little linear algebra. So in particular, when you have a scalar factor in a column, linear algebra tells us that you can factor out that scalar factor. And here's another column with a scalar factor that we just factor right out. And then the one tricky bit, the one part that is sort of a way of what just happened here, I claim that this matrix is the derivative matrix, dg, and where on earth did this come from? So this is you could write it out in coordinates and it works and it's fine, but I think it's a little bit more elegant to see it as follows. If I want to understand this matrix here, a great way to understand a matrix is to understand the columns of the matrix. So let's look at this first column. The first column is dg applied to the standard basis vector E1. Now, looking only at this first column, let's remind ourselves, hey, what happens when you take a matrix and multiply by a standard basis vector? One of our cornerstone facts of linear algebra. Matrix times standard basis vector gives you the corresponding column of the matrix. So, altogether then, what we've just argued is that the first column of this matrix is, looking at this expression, the first column of dg. Analogously, the second column of this big matrix, looking at the formula for it, analogous argument, is going to give me the second column of dg. So this matrix and the DG matrix have the same columns. And if these two matrices have the same columns, then they are the same matrix. So it's a nice little tricky little argument. It's all linear algebra. I don't want to focus on that because linear algebra is, of course, prerequisite of the course. But this is it's one of the necessary tools in finding this stretching factor, namely by what factor that I had previously just asserted do we multiply input area to get output area. And we see here that that factor is as claimed. So there you go. All right. Now, what about 3 dimensions? Every change of variables question we've done so far has been in 2 dimensions. So if you're in 3 dimensions, and, look, I might find myself sometime having to compute an integral over this monstrosity of a domain. And you might entertain yourself with the horrors of how brutally difficult it would be to slice this up. You're going to be hitting corners and side-swiping faces and all sorts of weird things. This is, I mean, in effect, impractical. Almost impossible. So the big idea, just like in 2 dimensions, is to view that as being an image by way of a known function of a more desirable domain, such as a box, such as here, and then just make a pullback argument. And everything works just fine. All good. Go ahead. Do the pullback. Plug in. No problems at all. The only little asterisk is we have to think about the stretching factor. The stretching factor formula turns out, again, to be the absolute value of the Jacobian determinant. Now, the argument for this, I'm going to leave as an exercise for y'all. It is morally equivalent to this argument. Almost exactly the same argument. The only difference being that here we had a 2-dimensional parallelogram being an image of a rectangle, and in 3 dimensions we would need to talk about a 3-dimensional parallelepiped being an image of a 3-dimensional box. But it's still going to go down by edge vectors. It's still going to be a packed formula for how to compute a volume, now a parallelepiped in 3 dimensions instead of parallelogram in 2 dimensions. And that is still going to go down as a determinant. And appropriate other dimensional adaptations, and other than that, it's basically the same argument. So, great little exercise for y'all. And again, as always, if you get stuck, come to office hours. Very happy to walk you through it. But the ideas in this 2-dimensional argument will allow you to justify for yourself why this is the stretching factor in 3 dimensions. Okay. So give that a try. Here's a cool fact that is preliminary to the example we're just about to do. So let's just get this established first. It's a nice little fact. In fact, we've noticed this already in a previous example. The theorem says that if you have a matrix that you use to define a linear transformation, T, and then if you take the derivative of that linear transformation, the derivative matrix will be the same original matrix. That's kind of convenient how that works out. Easy to prove. I'm going to suggest you only prove this in 2 dimensions because it's kind of, you'll notice the pattern. It's pretty clear what's going on here. Just write down an arbitrary matrix, A, B, C, D. Multiply out and get the formula for the resulting linear transformation T. Take the appropriate partials to write down the derivative matrix, and behold, it is going to be the same A, B, C, D. Right? So easy little argument. Give that a try. Again, write it down. Think about how to write it down. And come ask questions if you get stuck. Okay, armed with that, let's now look at this example. This is going to be a 3-dimensional change of variables. Our domain here for our 3-dimensional integral that we're starting off with is this parallelepiped. And before we get to actually cleverly addressing this, let's just take a quick moment to again bask in the horrors of how hard it would be to slice up this domain. Now, it doesn't look that bad. It's got nice flat faces and stuff, right? But if you think about it, as you start slicing that, there's going to be a first slice that's going to be on a vertex. There's going to be a last slice that's probably going to be at a vertex. There's 6 other vertices. They're going to be in the middle. You're probably going to have 7 separate integrals here. And what's worse, each of those 7 separate integrals itself is not a rectangle, right? You look at those slices. Let's see if I can do this. If you look at one of those slices, it could cut through multiple of these faces. Like one of these slices might, might be like that. I don't know, something like that. Right, this parallelepiped's all kind of wonky and stuff, right? It's not aligned with any of the coordinate planes. So you're going to have some weird slices, meaning that of those 7 integrals, each one of those is going to break up into several integrals, depending on what these vectors are and how the angles work out. But so it could be as bad as, you could have like 20 or 30 separate integrals here. This is a nightmare of inconvenience. Everybody see why this is scary? Yeah. Okay, so let's talk about how to address this feasibly. The strategy is to use a certain trick. I emphasize this is not a follow your nose trick. This is very clever. This is an insightful bit of cleverness that got thought of a long time ago, and everybody's been copying that move since then. I don't know exactly how long. I would guess it's been a couple hundred years probably. It's been a long time. Here it is. The clever move. The edge vectors. Hang on. Be in highlighter mode. Here we go. The edge vectors that define your parallelepiped that are given, make those the columns of your matrix. That matrix, then, you use to define a linear transformation. Use that as your change of variables function. That's, I claim, a wonderfully powerful, wonderfully effective choice. So you got to remember, though, what the clever move is take your given edge vectors, right? Make those the columns of your matrix. Now, let me explain why this is a good choice. Like, how does this make all those horrors disappear? And I claim what's about to happen here is, as we look at this unit cube, if I were to ask what is the image of this unit cube, I claim it's going to be our parallelepiped. Said differently, our pullback domain is just going to be the unit cube. Before I explain why, let's take a moment to appreciate how awesome that would be, right? Nightmare of 20 or 30 separate iterated integrals turns into everybody's favorite domain for a triple integral. 0 to 1, 0 to 1, 0 to 1. Can't get any nicer than that. Okay, so how do I know this is true? Well, we understand parallelepipeds by their edge vectors. Let's look at E1. Let's ask, where does that edge vector go, E1? Well, if that E1 goes into our linear transformation, then that's what we're going to multiply by our matrix A. Now, what happens when you multiply standard basis vector times a matrix? Again, one of our basic facts from linear algebra. Matrix times standard basis vector gives you the corresponding column, which we have cleverly arranged to be our parallelepiped's first edge vector. Right, so totally awesome how this works out. This first edge vector of the cube goes to the first edge vector of the parallelepiped. Likewise, the second, third edge vectors go to the second, third edge vectors, and then by linearity, the cube as a whole goes to the parallelepiped as a whole. So it worked out just as we would hope. Right? And now it's all over but the shouting. All we have to do is say, well, with this change of variables set up, this integral on that horrifying domain pulls back to this integral on this lovely little domain. And all we have to do is, plug in the formulas. Yeah, sure. But we have, the only little non-obvious thing we have remaining, don't forget to add your stretching factor. Super easy to forget. Very, very important in the computation, of course. So don't forget to take that determinant and stick it in there. How we doing? Is everybody all right? Okay, great trick. All right. Okay, so moving along. We're going to go to the next kind of, well, it's not the next section. By the way, I think I commented on this before, but there's a few sections in this book that are monstrously big. Eyebrow-raisingly big. Like, how come this didn't get broken up into 3 sections? That kind of thing, right? It's weird, but anyway, if it were up to me, this would be a separate section. This whole idea of doing integrals and coordinate system would be a whole new section. But the way this book is written, there's just this massive, gigantic single section. Okay, anyway, here we go. Recall, we talked a long time ago about coordinate systems, right? Polar coordinates, cylindrical, spherical. We talked about how they're functions. And I'm just going to make the, unremarkable, I think, suggestion that, hey, we have a function here that goes from 2 dimensions to 2 dimensions. I can use that as a change of variables function. I mean, sure, why not? You totally do that. It's just like any other change of variables function we've used previously. It's just that, it's not clear yet what domains this is going to be useful for, but we are perfectly welcome to call this a change of variables function. Likewise, cylindrical coordinates goes from 3 dimensions to 3 dimensions. This can be a change of variables function in 3 dimensions. Likewise, spherical coordinates, right? 3D to 3D, same deal. All right, so if you're going to use these functions as change of variables functions, you got to compute the stretching factor. So we start by computing the Jacobian determinant, ends up being R. Our stretching factor, don't forget, is the absolute value of that Jacobian determinant. So there you go. By the way, you should fill in these blanks. A little bit of algebra, not that bad, take you 2 minutes. Likewise, cylindrical coordinates, yada, yada, yada. Now, this is a 3x3 matrix, but there's several zeros in here. This determinant ends up being basically the same computation as polar, not surprisingly. And so, again, stretching factor is going to be the absolute value of that. And then the one that's a little bit different, spherical coordinates. This is a weirder, the algebra works out less nicely. There's quite a bit of trig that goes into this. This is probably 5 minutes of trig. But I think this is a healthy exercise. I hope everybody will take a crack at this. It'll only take you 5 minutes. Everyone should do this once in their lives. It's not that bad. You'll see several very convenient opportunities in this calculation to use Pythagorean identities. It's pretty nice. And there's the answer. You get rho squared sine phi. So, like I say, good exercise. For whatever it's worth, this was a test question about 5 or 10 years ago. So, healthy exercise. Okay. Okay, so last thing now, what are we going to do with these absolute values, right? If I have to, every time I want to use polar coordinates as a change of variables function, am I really going to have to insert into my integral an expression that has an absolute value in it? I hate absolute values. Super annoying. Right? Nobody likes absolute values. So how can we get rid of that? And here's where we make a choice. That's going to save us that inconvenience. The choice, and I emphasize this is a choice. You don't have to do this. We have not previously done this because we had no reason to do this. But we're now going to, for our own personal benefit and at our own will, we're going to choose only to use non-negative values of R. We are, therefore, correspondingly, promising we will never anymore use any negative values of R. Previously, we left ourselves that possibility because we had no reason not to. Now, though, making this choice, choosing R always to be positive, notice that the absolute values effectively become irrelevant, and the absolute value of a positive number, of course, is that positive number. And now our stretching factor is just R. Okay, so if in other contexts you've seen, polar coordinates R has to be non-negative. I mean, it didn't really have to until now. And now we choose to do it for a legitimate reason. How we doing? Everybody cool? Okay, so likewise with cylindrical coordinates, we're going to choose only non-negative values of R. Again, it's a choice. Again, in so doing, our stretching factor becomes just R, and that's nice too. And now a lot of students get the next one wrong. A lot of students figure by analogy that, hey, you know what, rho kind of plays sort of the role that R did. A lot of students figure, okay, well, as long as I promise I will only choose positive rho, then I can lose the absolute values. And look at how that doesn't work out, right? Knowing that rho is positive, can I conclude that everything else inside of here is positive? Not even close. In fact, it's pretty useless to make promises about rho. Whatever rho is, it's going to get squared. It has nothing to do with whether this expression is positive or negative. So forget about rho. What we need to worry about is how can I ensure that sine phi is not going to be negative? That's the concern. And what do I do to phi to ensure that this will never be negative? I just have to choose phi to be between 0 and pi. That allows me to conclude sine phi is going to not be negative, and therefore the absolute values go away. So, like I say, don't figure, by speculative analogy. It just doesn't work in this case. Phi is the issue. Now, what have we lost here? Is this going to be a problem for us? How annoying? How much of a sacrifice is this? And I propose is not at all a sacrifice. These are our favorite values of phi anyway, right? Personally, I find it super inconvenient to have to consider values of phi that are not between 0 and pi. So the upshot of this is, hey, if you promise to only do what makes your life easiest in the first place, then you get the added benefit of the additional convenience of not having to worry about the absolute values. So this is a big win-win, right? So do make sure to keep all that in mind. Okay. So let's get one in the win column here. Here's an integral on a domain. My domain is like so. The integral, therefore, is that. Now, before we do this the clever way, let's speculate on how nasty this would be if we just kind of went, head on, tunnel vision. We just started slicing this up a la section 5.2. Here's what your integral turns into. Notice, square root on your inner bound. Square root comes from the fact that this circle in rectangular coordinates, this circle's equation, when you solve for y, you get a square root. And this integral, because of that square root in the inner bounds, is not nice. It's doable, but it's not nice, right? This is inconvenient. Trig substitution or a very clever integration by parts followed by other work. This is an irritating integral to have to deal with. Okay. So that's what we're hoping to avoid. I'm going to claim, to be justified in a second, that if we use the polar coordinates function as a change of variables function, I claim that our pullback domain is going to be this rectangle. Nice, convenient rectangle. And now, again, I've got to justify that, but let's just kind of notice that means that this nasty integral right here that I had to deal with because of this shape, if I pull back through the polar coordinates change of variables function, now I get an integral whose bounds are constants because it's a rectangle and life is much better. Okay. Now, so I owe you an explanation. Why is it that this is the pullback? And let's just think about the edges here, sort of one at a time. Let's look at this edge, right there. That edge, you can see right here, this is where r equals 1, between where theta equals 0 and where theta equals pi over 2. Well, in the xy plane, that's that. R equals 1. Between theta equals 0 and theta equals pi over 2, right? So this edge goes to that edge. And you can sort of think through the rest of them. And again, you can. This is a good exercise for you all to think through on your own. You know what? That looks too similar. Let me use green. This edge right here goes to that edge right there. This edge. Now, every point on that edge is on r equals 0. That whole edge gets kind of pinched down to just the origin. And then, color choices. We'll use yellow here. That edge goes to that edge. So, sure enough, the image of this rectangle is our quarter disk. And we can play pullback games, and it's all downhill from here. Everybody all right? A couple of little details we have to remember. Again, easy to forget. Let's see here. Let me zoom just a little bit. Come on. Here we go. So as we do the remaining plugging in, don't forget that x squared plus y squared, I've got to rewrite that in polar coordinates. Luckily, that's a freebie. Normally, we would expect to have to plug in the formula. X equals r cosine theta. Y equals r sine theta. And you can do that if you like, and you will get r squared, but you can also just remember we have a existing, one of our standard formulas is x squared plus y squared is r squared. So that's the plugging in. Don't forget to add your stretching factor. On the previous page, we've already justified that the stretching factor is r. Notice that we have lived up to our promise. We have only selected values of r that are non-negative, right? We didn't venture into the left side of the r theta plane there. And it's all downhill from here. Nothing to it. Our integrand is r cubed. The antiderivative, 1/4 r to the 4th. Single variable calculus. Answer's pi over 8. Everybody happy? All right. Now let me point out one other thing that happened here. Looking at this pullback domain, notice I had to do the appropriate slicing. So theta starts at 0, theta ends at pi over 2, and then I have to focus on a given theta slice. And on that theta slice, I notice that r starts at 0 and then ends at 1. Okay. Here's the slick move now. All that slicing that I did, that I just kind of swept under the rug previously. Theta slicing, for example, looks like this. A theta slice, of course, means a slice representing a constant value of theta. And here's the good news. I know exactly what that looks like in the xy plane. Right now, to be fair, when you've done the pullback, your integral is actually happening over here. It's actually happening on the pullback domain. But again, all you really need to know about that pullback domain, coming back up here, all I need to know about this pullback domain is what are the resulting bounds. The bounds come from just being able to understand the slices. So if I can see the slices in the existing picture that I was given at the start of the problem, I don't even have to draw the pullback domain. Everything I need to see about it, I can see over here already. So let me show you how this plays out then. This is the exact same example. Same, first quadrant portion of the unit disk, same pullback, same polar coordinates, change of variables. Exactly the same. I'm just going to do this whole thing now without making any reference to the pullback domain. By just observing that, okay, well, I know that my theta slices look kind of like this. I can see that my first and last theta slices are at 0 and pi over 2. Because again, this is what theta slices look like. This is where theta is 0. This is where theta is pi over 2. You can see that right here in the picture. And yeah, I mean, full recognition. That is the actual theta slice where theta is 0. This is the actual theta slice where theta is pi over 2. But why do I have to draw a whole new picture when I can see them right there in my existing picture? Analogously then, let's see here, looking at an existing theta slice. So again, technically that's where the theta slice is on our actual pullback domain. But I can just as well imagine that represents this theta slice. And I can play first and last games in the usual way by, for example, at that point, well, that point's where r is pretty clearly 0. Now, sure, it is arguably also seen just as well from there, but why mess around with this picture if you can already see it in that picture? Similarly, this point here is on r equals 1. Well, yeah, right, and likewise, this point is on r equals 1. And you can see it just as well, in fact, arguably more conveniently, in your existing picture. So we don't need to draw the pullback domain at all. And in some sense, we also don't even really have to draw the fact that we're using specifically the polar coordinates change of variables function, because all we really need from that, aside from what do my slices look like, is the stretching factor. And the stretching factor we already have established is just r. So here's the beautiful little culmination of these sort of streamlinings. Even though, of course, we are doing a change of variables. I don't really have to say that or do that or even recognize that. I can just say I'm going to do this integral, what we call in polar coordinates, by inserting the appropriate stretching factor with my differentials and understanding my bounds based on the appropriate polar slices of my given domain. Everything I need I can see on the right-hand side there. Okay, let's see another example. Notice I'm not even drawing and scratching out. I'm not drawing in any way what the pullback domain is here. We're going to go, without a net on this one. And okay, well, my theta slices kind of look generally like this. That's what theta slices look like right? And theta, I'm going to imagine as starting right there where theta is 0, and it goes all the way around until we're done making our solid, or excuse me, our region, and then it ends having gone all the way around at 2 pi. I don't have to draw any pullback domain at all. Theta goes from 0 to 2 pi. Is that cool? Okay, likewise, for a given value of theta now, my starting value of r, there is the first, which you might call the first r point on my theta slice. That's the origin. That's where r, of course, is 0. My last point, my last value of r on this theta slice, well, it's on this curve, which is the unit circle, which means that curve is r equals 1. So my upper bound for r is 1. Boom. No pullback to draw. You can see it all right there on the XY picture. Okay, and then, yada, 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 details, make sure to do the integration. Also, make sure not to forget to insert the stretching factor. Of course, the stretching factor has to be there. All this business about streamlining the slicing process is a convenience. It doesn't change the fact that underneath all of this, there is, in fact, a change of variables. Change of variables does require that you stick that stretching factor in there. If you leave this out, then that's deeply inaccurate. And for whatever it's worth, also, let's just talk about how this manifests itself on exams. It's worth a lot of points. Now, you can think of this two different ways, right? I prefer to be a glasses half full kind of person. This one factor, r here, is really important to the extent that it's worth several points on an exam question. Depending on what else there is going on in the question, it could be as much as 5 points. Maybe it's only 3. But it's going to be worth several points depending on this and that. And it's all you got to do is remember to put it in there. It's that easy. Just know the formula for the stretching factor, stick it in there, boom, you just earned several points. Right? So this is don't leave money on the table situation, right? Make sure to remember to put that stretching factor in there. It is a very significant, non-trivial, sophisticated part of this whole idea of doing an integral in polar coordinates. And get that credit, because all you got to do is remember. That make sense to everybody? All right. Cool. Okay. Now we're going to do some more examples, but I want to hit some tips and tricks first. You do have 2 different choices as to how to order your differentials. Here's the good news. It's almost always best to use this order. I am not clear if I have ever seen a non-manufactured counterexample to this. Like, in other words, naturally arising in like physics or engineering or anything like that. Now, I can manufacture weirdo, unnatural examples. Yeah, sure. But vast majority of cases, that's the choice. So I would encourage you just to assume that should be the correct order. Just always do it in that order. Okay, next tip. Looking back up to this example, notice there's a bunch of attention that's going to have to be given to slices and ranges of values and starting and ending and all that business. And there's a bunch of sort of geometric thought that goes into it. And while all that's happening, you might inadvertently forget to stick in the stretching factor. I've done it myself more times than I'd like to admit. And I have seen students do this on exams a lot. Back of the envelope, ballpark, I don't have any data on this, but I'm going to say I feel like before I started making a huge pitch out of this, about 20% of the time, a lot of students would just they just forget because they're thinking about all these other things. So my trick for avoiding this, and look, it can happen to anybody. Oh, here it is. The way you can avoid accidentally screwing this up, always write down this whole thing all at the same time. RD theta. This is actually a really natural thing to do. DRD theta by itself, basically never useful. Right? If you're going to do an integral in polar coordinates, it is a change of variables. You will have that stretching factor. You must have R with the DRD theta. You might as well write it down at the same time. If you just make a habit of never writing down DRD theta without writing R first, that will help prevent the always possible accidental screw up where you forgot to insert your stretching factor and you leave money on the table, right? You just forgot. Happens to the best of us. Okay. All right, and then lastly, the procedure for finding bounds. They come from understanding certain points which are on certain curves which have certain equations which you solve to find what you need, just like in every other system. Okay, so here's a next example. Here we're going to look at this annulus, which I like to think of as a moat around a castle. I don't know why, I just like that. And let's suppose that's my domain. Right? How am I going to compute an integral on this domain? Now, a lot of people will tell you, okay, well, let's compute the integral on the entire disk, and then we'll subtract the integral on the inner disk. Right? So sort of green minus purple. And that's a very tempting suggestion, but I claim it doesn't work. This is all nonsense. And the reason why is that if you look at your integrand here, let's see, you know what, I will use a pencil for this. Your integrand is undefined at the origin. Completely undefined at the origin. That means that this green integral, undefined. Right? The only definitions that we have for an integral involve and require that the integrand be continuous, which means it has to be defined, among other things, but everywhere in the domain, and this function's not. So this is, you cannot write down that green integral. And likewise, you can't write down that purple integral either. Neither one of those integrals is defined. You may be thinking to yourselves, why not improper integrals? It turns out that improper integrals are not as simple in multivariable as they are in single variable. It's a really tricky business, and certainly not something we can address in this course. So this is a absolute no-go, dead in the water, can't do it approach. Okay, next thing you might think to yourself is, hey, how about I'll just chop it up into pieces, like that piece and that piece and that piece and this piece, right? And I guess you could do that, but again, nobody wants to do 4 separate integrals. And furthermore, if you think about it, each one of these 4 regions, the boundary curves, circles. And circles in rectangular coordinates, when you solve for one of the variables to get your bounds, will always give you square roots. So this isn't just 4 integrals. This is 4 ugly integrals. This is highly undesirable as well. Okay. Look how easy it is in polar coordinates. Nothing to it. Theta just goes all the way around 0 to 2 pi, just like another example we already saw. And then you fix a value of theta. And let's see here. It looks like R is going to start at that point, which is on that curve, which has that equation. Solve for R, and your inner R bound is that. And then R is going to end at that point, which is on that curve, which has that equation. Solve for R, and your upper bound is that. Up to it. Snap. World's easiest integral results. How we doing? Everybody happy with that? So really powerful trick. Having this option at our disposal of doing an integral in polar coordinates instead of rectangular coordinates. Very powerful computational trick. Okay. Here's another one. This is a weird set. We're going to look at this disk. And we're going to look at the part that does not include that disk. In other words, we're going to imagine a big bite taken out of our green disk in the shape of that red disk. And the result, of course, green minus red is this shaded region right here. All right, so everybody see that domain? Again, you could try to do this in rectangular coordinates. And again, it's going to have three pieces. It's going to have square roots in your bounds. No good in rectangular coordinates. So we're going to do a polar argument. We're going to think about theta slices. My theta slices, of course, coming out of the origin, that's how theta works. So my theta slices are like this, and there are several, sort of further back, like this slices. And we could talk about first and last. The first slice is going to be this point right here. Now, you could, this is perfectly fine, you could take that point, notice that it's on these two curves, find the equations, solve for theta. That works fine, no problem. But sometimes there's an easy little freebie that you can capitalize on, and I'm a big believer in capitalizing on conveniences. Notice that point is on this circle of radius 1, which means that this radius of that circle is 1. Likewise, that's 1 because that too is a radius of the same circle of radius 1. And then lastly, notice that this is a radius of that circle of radius 1, right? So nice little punchline is that by observing what's a radius of what, this point is on a known established equilateral triangle, and we already know the angles of equilateral triangles, and keeping in mind that this is sort of going in the negative theta direction, it's sort of going downward, right, from where we measure theta, this is just negative pi over 3. Let's see here. Here we go. So that angle, negative pi over 3. That's a slick move. Be on the lookout for this kind of thing. Be surprised how often little conveniences like that can pay off. Likewise for the upper bound. Think through for yourselves, but that upper bound point, again, that's an equilateral triangle for very similar reasons. And therefore, that angle, positive pi over 3. Okay. All right, now we're going to fix a value of theta. We're going to look at, for example, that theta slice, and we think about this point, which of course is on that curve, which has that equation, thus giving me my lower bound of 1. And then my upper bound, let's see, is going to be that point, which is on that curve, which, yikes. Okay, this is a less obvious curve, right? It's an off-centered circle, but not that hard to take roughly this equation, right, and convert to polar coordinates a la chapter 1. And so that's the equation of that curve. Solve for r. And you get that. Is that cool? Everybody happy? Okay. Last comment, super quick. Notice that even though I didn't say so, you just have to take my word for it here, but when I wrote all this down, I claim I did write down that R at the same time that I wrote down the dr d theta. Again, I urge you don't have to. If you want to gamble with your score, you're welcome to take the risk. It's up to you. But I urge you, always write down r dr d theta all at once. It really helps keep you from forgetting it. All right, see y'all later. Have a good one.